relation between the rate constant and temperature. In the previous parts, we talked about the rate constant. The rate constant for two different reactions is in general different. The rate constant of several experiments of the same reaction is temperature dependent. So what is the relation between K and temperature? The rate of reaction are highly sensitive to temperature. When the temperature increases, we give energy to the reaction system. So the molecules will absorb this energy as kinetic energy, and they will move faster. So we will have more collisions between molecules, and in this case, the rate of the reaction increase. So most reactions go faster at higher temperature. It implies the rate constant almost always increase with the temperature. The rate constant, the rate law expression is given by R times concentration at A to the power M times concentration to B to the power N. We said that M and N are the partial orders that explain the effect of the change of the concentration of A and B respectively on the rate of the reaction, and K is a function of the temperature. In the same reaction, in the same experiment, we could not change the temperature. When the reaction starts at 25, in order to study the kinetic of this reaction at this temperature, we should not change the temperature. So K is a function of the temperature. And in the same experiment, the temperature is constant. For this reason, K is called the rate constant. For the same reaction, the rate constant is related to the temperature according to Arrhenius equation. K equal A, pay attention, A, the notation A, italic A, is not the reactant A. This is another notation, but called A. K equal A E minus EA divided by RT. In this relation, in Arrhenius equation, we see the variation of K as a function of the temperature. I will explain what is the meaning of EA and A. So the rate law expression is given by R equal A, which is the steric factor. This is not the reactant A, the steric factor, E minus EA divided by RT times A to the power M, B to the power N. I will pass to the explanation of Arrhenius equation. According to Arrhenius equation, K equal A E minus EA divided by RT. What is EA? EA is the activation energy of the reaction. By definition, it's the minimum amount of energy required to initiate a chemical reaction, and the unit of EA is in kilojoule per mole. Suppose I mix A with B. We will have collision between A and B, and these collisions will produce, for example, a 30 kilojoule per mole. If the activation energy of the reaction is 35 kilojoule per mole, what is the meaning? That means this reaction would not proceed if the collisions between particles did not give minimum 35 kilojoule per mole. It needs at least 35 kilojoule per mole. So if the collisions release or give 30 kilojoule per mole and not 35, so this reaction would not proceed. The activation energy is the minimum energy needed in the reaction to proceed. And the activation energy of a reaction is constant, is well defined. We will see that the addition of the catalyst only change the activation energy of a reaction. What is A? A is different from the reactant A. This is a notation. A is the frequency factor or the steric factor given in m-1 second minus 1. This is the frequency of collisions with certain orientation when the reactant concentration is equal to 1 molar. Pay attention that for the same reaction at different temperatures, A, the steric factor is the same. In other words, when you mix A with B, the collision between A and B depend on the orientation and A and that of B. According to this orientation, if A is directed to B, the probability of reaction increase. But if A is directed inversely in other direction, so the probability of the reaction between A and B decrease. So A is a property of the reaction. A is a certain constant in the reaction. For the same reaction, whatever is the temperature, the steric factor, or the frequency factor is constant. And in general, we give the frequency factor of the reaction. So this is given. T is the temperature of the reaction in Kelvin. So according to Arrhenius equation, the rate constant of the reaction depends on the activation energy of the reaction, which is constant, which is given, depends on the steric factor or the frequency factor of the reaction, which is given, is constant. So K is only temperature dependent for a certain reaction. And R is the ideal gas constant equal 8.314 joule mole minus 1 Kelvin minus 1. Activation energy and the activated complex. To remember that for a certain reaction, without addition of a catalyst, for a certain reaction non-catalyzed, the activation energy of this reaction is known, is constant, and the activation energy is the minimum energy needed for the reaction. So the value of the activation energy is always positive. Suppose in a question, they ask to calculate the activation energy, and you find that the activation energy is negative, that means your work is incorrect. The activation energy should be positive, and the activation energy unit is in kilojoule per mole. What is the activation energy relation and the activated complex? In a certain reaction, when we mix A and B, we obtain C and D. We start with known reactants and we obtain known products. But we don't know what happened in the transformation between the reactants and the products. So when we mix, for example, hydrogen and oxygen gas to obtain H2O water, the first step in the reaction is to have collisions between O2 and H2. and look to this figure, the orientation of H2 with respect to O2 is well known, so the steric factor or the frequency factor of this reaction is known. We will have collisions between these particles, so the energy will increase. The energy will increase till the maximum. Before this part, from the beginning, from this point to the end, to the top, we don't have a product formed. We have only reactant in collisions. So the energy will reach a maximum, then the energy will decrease due to the formation of water molecules. At the top of this curve, we have maximum energy. So we have formation of intermediate. We don't know this intermediate, but we have formation of intermediate of high energy. This intermediate is unstable since the energy is great, and the intermediate is called the activated complex. Why activated complex? Complex since it's a certain relation between H2 and O2, but we don't know the stoichiometry of this complex. Activated since the formation of this intermediate will release the products. For this reason, this is the activated complex. By definition, the activated complex is unstable intermediate between the reactants and the product, and when we reach this activated complex, we may have formation of the product. So what is the activation energy of the reaction? By definition, the activation energy of the reaction is the energy needed to start a reaction. So this is the energy needed to reach this point. So the difference between in a blue arrow, this difference of energy is the activation energy of the reaction. In other words, the activation energy of the reaction is the difference of energy between the activated complex and the energy of the initial reactants. In this curve, in this graph, we observe that the energy of the products is less than the energy of the reactant. That means the products are more stable than the reactants, and the difference of energy equal E product minus E reactant will be negative. So this reaction is exothermic. If the energy of the product is greater than the energy of the reactant, that means the reactants are more stable and the reaction is endothermic. The activated complex is a highly unstable species with high potential energy. The activated complex is unstable. This is the intermediate between the reactants and the formation of the products. The activation energy is the amount of energy needed to convert reactant into the activated complex. So this is the difference of energy in the blue arrow. The activated complex is a chemical species with partially broken and partially formed bonds. In general, we could not identify the type or the nature of the activated complex since this activated complex is unstable. What is the meaning unstable? So we could not isolate it in order to analyze. So the activated complex in most reaction is unknown. How to calculate the activation energy? According to Arrhenius equation, the rate constant of the reaction is related to the frequency factor or the steric factor, the activation energy, and the temperature of the reaction. For the same reaction, A and EA are given, are known, are constant. So the rate constant is only temperature dependent for the same reaction. Implies ln A equal ln K equal ln steric factor ln A minus EA divided by RT. To calculate the activation energy of a certain reaction, and this is the experiment done in the laboratory. This is the main method to find the activation energy of a certain reaction, is to go to the lab to realize the reaction, the same reaction at different temperature. So you did several experiments for the same reaction at different temperature. For each temperature, you can find by the 4 method we used previously, we can find the rate constant K. So you obtain at T temperature T1, you obtain K1. At temperature T2, you obtain K2. At temperature T3, you obtain K3. At temperature T4, you obtain K4. But pay attention, in all experiments, A and EA are the same, since you have the same type of reaction. So you have a table, the variation of K as a function of the temperature. Draw ln K as a function of 1 over T. You will obtain a straight line. You will obtain a straight line when you draw ln K as a function of T, and the slope of the line is equal minus EA divided by R. So you can calculate the slope of the line. R equal 8.314 mole minus 1 joule mole minus 1 Kelvin minus 1. So by this way, you can find the graphically or experimentally the activation energy of the reaction. And for 1 over T equals 0, ln K equal ln A. So the intercept with the y-axis is equal to ln A. And you can find also graphically or experimentally, you can find the frequency factor or the steric factor A. So this is the general method to calculate or to find the activation energy of a certain reaction. Example 7.7. Determine the activation energy and the frequency factor for the reaction O3 gas to O2 gas and O gas, and given the following data. So he realized in this example 7 experiments at different temperatures. So we have the same reaction in 7 experiments for the same, in 7 experiments at different temperatures. So K is not the same. K is variable since the temperature of the reaction has been changed. For example, at 600 Kelvin, 3.37, 700, 4.83. Look, as K increase, as the temperature increased in Kelvin, at the temperature increase, the rate constant increase, and this is what we talk in Arrhenius equation. When the temperature in most of the chemical reactions, when we increase the temperature, the rate constant increase. So we have a table at different temperatures, 6, 7, 8, 9, 1000. Then he did more experiments. So we have a table. In the table, we have the variation of the rate constant as a function of the temperature. What we do? We draw ln K as a function of 1 over T, and not K as a function of T. We draw ln K in Arrhenius equation. We draw ln K as a function of 1 over T. So we obtain a straight line. The slope of the line equal minus 1.12, and the slope of the line is equal minus EA divided by R. the slope of the line equal minus EA divided by R. So minus EA divided by R equal minus 1.12 times 10 to the power 4. So we obtain the activation energy 93.1 kilojoule per mole, and pay attention that the activation energy value should be positive. And we can calculate also ln A, or we can calculate the frequency factor A for 1 over T equals 0, ln K equal ln A. So we calculate by this way, A 4.36 times 10, 11, m minus 1 second minus 1. This is an experimental procedure to calculate the activation energy. So for the same reaction, K depends on the temperature. At temperature T1, we obtain a value K1. At temperature T2, we obtain a value K2. The relation between K and temperature is given according to Arrhenius equation, K equal the frequency factor A, E, minus EA, which is the activation energy, or the ideal gas constant, and T the temperature. So apply this relation on two different temperatures. We can write K1 equal A E minus EA divided by RT, 1, and K2 equal the same A, since we have the same reaction, E minus EA, the same activation energy, since we have the same reaction, divided by RT2. So divide now, K1 divided by K2, we eliminate A with A, we obtain K1 divided by K2 equal E minus EA divided by RT1, divided by E minus the same EA, the same activation energy, since we have the same reaction, divided by RT2. So K1 equal K2 EAR T1 minus T2 divided by T1 T2, and we did log for log K1 divided by K2 equal EA divided by R 1 over T2 minus 1 over T1, or in other words, we can write ln K2, if we inverse K2 divided by K1 equal minus EA divided by R 1 over T2 minus 1 over T1. You can use one of this relation. Ln K2 divided by K1 equal minus EA divided by R. If you put minus, you start by T2, T1. Okay. Or ln K1 divided by K2 equal plus EA divided by R1 over T2 minus 1 over T1. This is an important relation that allows to calculate the rate constant at temperature T2 if we know the rate constant K at temperature T1. Example 7.8. The reaction NO2 gas plus CO gas to CO2 gas and NO gas has a rate constant K 2.57 m minus 1 second minus 1 and rate constant 567 m minus 1 second minus 1 at T2. Find the activation energy. First of all, look to the unit of K. The unit of K at T1 is the same unit of K at T2, since the unit of K is related to the order of the reaction. And in this case, since the unit of K is m minus 1 time minus 1, so this reaction is of second order. But this is not requested in this exercise, but only I explain how to find the global order of the reaction. So at T1, 701 Kelvin, you have K1, and at T2, you have K2. You apply the relation. ln K2 divided by K1 equal EA divided by R 1 over T1 minus 1 over T2. Or I prefer to use K2, K1, T2, T1, so you put minus. Ln K2 divided by K1 equal minus EA divided by R1 over T2 minus 1 over T1. Pay attention that T1 and T2 should be in Kelvin. R in joule mole minus 1, Kelvin minus 1. K2 and K1 have the same units. So you obtain EA in the same unit of R. So in joules. Then you transform it to kilojoule. So the activation energy is equal 1.45 10 to the power 5. So 145 kilojoule per mole. And this is the activation energy. And the activation energy is always positive. Pay attention that the value of the activation energy tends to hundreds. So it's in the 100, 35 kilojoule, 70, 80, 100, 150. The value of EA is in tens to hundreds and not more.